Welcome back everyone. In this lecture, I will start with Fourier analysis on finite groups. So, initially we will focus on finite abelian groups, then later we will see how to actually generalize Fourier analysis to general finite groups. So, let us start with some motivation. So, let us recall the classical Fourier analysis. So, Fourier invented this continuous version of Fourier analysis in 1800s to study the heat equation. So, I am going to be very brief about the classical case. So, the most important thing about the Fourier analysis, like you can see that given two absolutely integrable complex valued functions, so we define the convolution product. So, that is actually important piece that we will be using even in the finite group Fourier analysis. So, let me just recall that. So, let us say we are given two absolutely integral complex valued function f and g. So, f and g are functions from let us say R to C, both are absolutely integrable complex valued functions. So, then the convolution product of this function is defined by the following formula. So, you take this f star g and then at the value x is defined to be the integral minus infinity to infinity f of x minus y g of y dy. So, now note that in this formula, so the important thing that we use is that this R being a group. So, the R with respect to the additive, this is indeed a group. So, here in this formula the group translation is used. Basically, this corresponds to x y inverse in R plus. Okay, so, this is something should be noted, because this very similar formula we will be writing it for finite groups as well. So, now given this absolutely integrable function f, the Fourier transform of f is defined as follows. So, recall the Fourier transform of f is given by f hat of x, such which is defined to be the integral minus infinity to infinity f of t e power minus 2 pi I x t dt. Okay. So, the important thing about the Fourier analysis that so once we define this Fourier transform of f, then we have this Fourier inversion. So, given f hat, so we will be able to recover f. So, that is the most important part of the Fourier analysis. So, indeed the Fourier inversion says that f of x can be given as integral minus infinity to infinity f hat of t e power 2 pi I x t dt. Okay. So, one can recover f more or less from f hat. So, that is the upshot of Fourier analysis. Indeed, if you think about it, the Fourier transform actually convert the convolution product to the pointwise product. We also have that f star g hat, the Fourier transform of this f star g is indeed given by f hat dot g hat. So, this also holds at the level of continuous functions. So, this is indeed motivated from understanding the heat equation, the Fourier transform and so on, they are defined. And later they have been used lot in many applications. For examples, they find applications in signal processing and image processing and so on. Even in other branches of mathematics like statistics, combinatorics and number theory, Fourier analysis used a lot. So, what we are going to do, like we will take this prototype that is available for the continuous functions, and then we will emit that for the functions defined on the groups. Okay. Just to introduce what we meant by that, let us actually try to do Fourier analysis on the finite cyclic groups first. So, if we think about it, the main goal of the Fourier analysis that so somehow we have this Fourier transform f hat, that is what given to us, and then from that we should be able to actually recover f. Okay. So, in somewhat very vague terms, like that can be made actually very precise. So, let us say like we have actually some wave function that is defined, let us call it as f. Okay. So, here is the motivation. Let us say f is the wave function. So, I am not going to be very precise about all these things, but given these wave functions, so this Fourier transform f hat, so that will actually corresponds to the wavelength. So, this will correspond to wavelengths. So, now in practice what we will do, actually one sets 0 to all sufficiently small values of f hat. So, thereby compressing the wave. So, this f hat in a way like this is what we are indeed recording. So, to recover this f, so the motivation is to recover f. So, we want to recover f from f hat. But in practice, like I said, so we may actually have some small wavelengths, so which are actually can be ignored, because as far as human eyes and ears are concerned, so those small wavelengths they do not play any role. So, then if we are interested in actually recovering f, so it is actually enough to recover f somewhat most appropriate f, that is good enough for us. So, if we start with this f hat which corresponds to the wavelengths, and by setting 0 to all sufficiently small values of f hat, so then using the Fourier transform, so we get the wave function that corresponds to the one that actually that we started with. More or less approximately we get the close enough wave function which is good enough for us for all practical purposes. So, the Fourier inversion exactly used to go back from starting with wavelengths to this wave function. So, this is where we are using the Fourier inversion. So, this is something we want to make it very precise for at least for groups. Okay, let us actually focus on this finite abelian group, finite cyclic group, and then make everything very precise. So, for that purpose, let us start with the periodic functions. So, it is very clear that an element in this c power g modulo n z. So, recall that this is the function space. This is all functions from z modulo n z to c. So, complex valued functions from z modulo n z. So, now given this function, you can see that this function actually bijectively corresponds to what is called periodic function with period n. So, let us define what is that. So, what is periodic function? So, a periodic function, it is a function from z to c such that f of x takes the same value as f of x plus n. So, this is said to be periodic with period n. So, then if it satisfies this condition that f of x equal to f of x plus n for all x in G. So, now this is actually indeed a discrete version of what you have seen in the basic Fourier analysis course. Usually we talk about functions defined from R to C that has period, let us say capital T. Suppose that T is 1, then that would actually corresponds to functions from the closed interval 0 comma 1 to C. Okay. So, suppose f is a function from R to C such that f of x equal to f of x plus 1 for all x in R. So, this indeed corresponds to a function from the closed 0 comma 1 to C. Okay. So, this is the classical picture. So, here we are actually looking at the discrete version of that. So, that means we are looking at the functions from z to c such that satisfy this periodicity condition. Okay. So, then it is easy to see, maybe I will leave it as exercise, that there is a bijective correspondence between the set of periodic function with period n and the elements of this c power z modulo n h. So, if we take this set of periodic functions with period n, so then there is a natural one to one correspondence between this and c power z modulo n h. Okay. Indeed, if you think about it little bit more, so whatever the structure that we are going to put it here, for example, vector space structure will be carried to the here as well. So, this correspondence actually preserves all the algebraic structure as well. But anyway, that will be very clear, like once we establish this bijection, I am not going to get into that. But now what we are interested in, so we want to kind of given a function f. So, we want to define its Fourier transform, and more or less we want to say that the Fourier transform encodes everything about the given function. So, in this case it may actually become or sound very simple, but the real difficulty is how to generalize this simple observation to the finite groups. So, before getting into the finite groups, let us focus on the cyclic groups and then see what really happens. So, recall that we already have this characters of this z modulo n z that forms an orthonormal basis for this space of this c valued functions from z modulo n z. So, recall. So, this space z modulo n z, which is same as the space of class functions on this z modulo n z. So, why it is true? Because both the group is abelian. So, there is no difference between class functions and the c valued functions. So, now if we take these characters, let us call it as chi 0 etcetera chi n minus 1, these are all the characters. So, let us say G is our z modulo n z, and these characters live inside z modulo n z hat, where G hat are nothing but those group characters from G to C star. So, because all irreducible representations are one dimensional, so the irreducible characters corresponds to the group characters from G to C star. So, now if we list this chi naught etcetera chi n minus 1 to be all irreducible characters of Z modulo n Z, and recall that how this chi I defined. So, chi let us say k of this at the value m is defined to be e power 2 pi I k m divided by n. So, this is a function chi k from G to C star, which takes the value on the coset bracket m equal to e power 2 pi I k m divided by n, and this is defined for 0, 1 etcetera n minus 1. So, now what we know that these chi naught etcetera chi n minus 1, they form on orthonormal basis. So, this is gives us orthonormal basis for the space C Z modulo n Z. So, in particularly once we have this orthonormal basis, then any given function, so any given function f from Z modulo n Z to C, so we can write in terms of this orthonormal basis. So, basically we are changing the basis from the delta x to this orthonormal basis. So, that means, so this given f, we can write f equal to some linear combination of this chi I. So, the coefficients will be given by exactly the inner product f comma chi naught plus etcetera plus f comma chi n minus 1 and then chi n minus 1. So, this is how we can write any given function. Since chi i's they form on orthonormal basis. So, f is linear combination of chi I whose coefficients will be given exactly by the inner product f chi I. So, now this already tells if you are interested in recovering f, it is enough to actually record all the values the inner product f chi I. So, basically Fourier transform encodes this information. So, you have this f which is given by summation f chi k ranging from 0 to n minus 1. So, you can easily see that to record f, it is enough to record these coordinates f chi naught etcetera f chi n minus 1. Okay. So, now we want to record this. So, we record it as the Fourier transform of this f. So, we define this Fourier transform as follows. So, the Fourier transform of f is defined to be, it is again a function from Z modulo n Z to C such that f hat at this coset bracket m is defined to be n times the inner product f comma chi m. So, know that this multiplying by n is just adjusting the scalar, it does not actually do any big difference, but so all we want to record is these values the inner product f comma chi m, and that is indeed recorded using this f hat. So, now if we rewrite this, you can see that f hat of bracket m is indeed exactly equal to using this expression. So, if you substitute here, so then it is exactly giving us which this f hat of m is equal to k ranging from 0 to n minus 1 f of bracket k and then e power minus 2 pi I m k divided by n. So, this is what we get. So, now let us go back to actually the continuous version. So, you can see that in the continuous version. So, we have taken this integral of f of t e power 2 pi I x t. So, indeed the discrete version actually, because there is no need to actually worry about the convergence and so on in the finite case. So, the integration is indeed replaced by the summation, and then we are keeping as it is the function f, and with that e power 2 pi I m k by n. So, indeed what we are doing actually, so these values, this e powers, they indeed corresponds to the irreducible character. So, this is something we will actually make it very precise later, and that observation and will help us to generalize the definition of Fourier transform to any finite group. Okay. So, now it is very clear that the function that we define, which is the Fourier transform, that is defined from the function space to function space, indeed it is an isomorphism of these spaces. So, recall we define this t, so which is a function from z modulo, sorry, the functions from z modulo n z to c to again complex value functions from z modulo n z, and how this function is defined, you take f and then send it to f hat. So, recall f hat is defined to be f hat of bracket m is exactly given by n times the inner product f chi m. So, now it is easy to see that since this inner product is linear in the way first variable, so that implies that this map T is indeed a linear map. So, it is clear that T is C linear map, and not only that, it is indeed an isomorphism. So, in particularly the Fourier transform is invertible, and given f hat, the f is given very explicitly using the f hat. Okay. So, what is the meaning of invertible? So, one can write down the inverse very explicitly as follows. So, now given f hat, sorry, given f, we have f hat. So, now in terms of f hat, the f is recovered completely. F is given to be 1 divided by n summation k range from 0 to n minus 1 f hat of bracket k chi k. So, this is exactly the equation that we started with. So, this is the equation star, and which is equivalent to this. So, this actually tells you that this map capital T is indeed invertible map from this function space to function space. So, that means given f hat, one will be able to recover this f. The Fourier transform on cyclic groups, so they are indeed used in signal and image processing. So, the idea is that the values of f hat correspond to the wavelengths associated to the wave function f, like I said before. So, one sets to 0 all sufficiently small values of f hat, so thereby compressing the wave. So, to recover something close enough to the original wave, so we just apply Fourier inversion. Okay. So, that is how it is used in practice. So, now if we think about it, this isomorphism indeed gives isomorphism between this algebra. So, this C z modulo n z also can be made into algebra, to this C n. Let me write it as follows. So maybe let me define the convolution product on CG. So one can define it for any group. Okay. So here is the convolution product. So the convolution product on CG. So let us take two functions f1g and cg. So fg both are functions from g to c. So now we want to define this convolution f star g. So which is a function again from g to c, which is defined to be at value x you take the sum such that f of x y inverse g of y, where y varies over g. So this is very close to the convolution that we had in the continuous case. So here we have written this convolution where we varied x and y, where we have taken f of x y inverse g of y. Similarly, we are actually writing the convolution even in this discrete case. So now it is a very simple exercise to see that this same sum can be rewritten as follows. This is summation f of x times f of y such that g of y such that this x y equal to z and then z varies over g. Okay, because the product here indeed x, oh sorry, the z is fixed. So we want to rewrite this as follows: f star g of x is equal to f of y g of z such that y z equal to x, where y and z comes from g. So this is another way to write this. Similarly, this also can be written as follows. You can fix the first coordinate as y, and then you can see that this y z equal to x. So then you multiply y inverse here. So then you get g of y inverse x here. Okay. So then this y runs over all g in g. So there are many ways to reinterpret the same convolution, and mostly we will use this definition for the convolution. And the important thing is that this convolution product indeed makes this CG into a ring. So this CG, the addition that we have already, and then we have this convolution product. So addition is the pointwise product, pointwise addition. So recall f plus g of x is defined to be f of x plus g of x for all x in g. So this is how the addition is defined, and the convolution product is defined with this formula. So with this one can see that CG plus star is indeed a ring, and if we count that vector space structure as well, so then that would actually tell you that CG is an C algebra. Okay. So I will actually verify that it is a ring, and we already verified it is a vector space. So that would give us that it is an C algebra. And what will be the identity element with respect to this star? So we have this delta E. So that is an element inside CG. So recall that. So delta x, where x in G. So delta x defined to be, it is a delta function at x. So for any given y. So, delta x of y is given to be 1 if x equal to y and 0 otherwise. So, this is the delta function, and when we will see that this delta E in CG is the identity. That means unit element multiplicative identity in this CG plus star. So, I will verify this in the next class. I will stop here. Thanks.